Surprise! Hey, yeah, so DJ Glenmo couldn't make it today, so he sent me, Professor Glenmo, his cuzzy bro from Kiwiland, to talk to you some more sort of deep tech stuff. So, yeah, another day playing with scripts and understanding module characteristics and a whole bunch of stuff. In fact, I even made a list for him, but he said, oh, you can do it. So I went, okay. So see if I can find the little list I made for him. But yeah, thanks everyone for tuning in. I can see a bunch of you, the regulars. G'day. Hi Charles. Hi Duke. Charles, are you up on top of a roof again, doing something dangerous while watching or listening to me? I hope not. So let's have a little look here. So what have we got coming up today? Yeah, so I'm going to get a bit more into the tech stuff again, and we're going to be looking at IV curves and understanding what is a double peak maximum power point. Why is it possibly a problem? Why do some inverters and charge controllers have solutions for double peak? And yeah, a bit of tips on design. What about maximum power point trackers, full stop? How do they work? And why are they better than a pulse width modulated control for regulating solar charge? We're going to look at understanding the effect of temperature on power from a PV module and how we calculate it, how we understand the effect of temperature on voltage, particularly open circuit voltage, but also at maximum power. And understanding why voltage drop equals power loss, and why that's important to consider. And yeah, dust and dirt. Now, I don't know if I can sprinkle some dust and dirt on this one, but yeah, that's another one, because we're actually covering off on some of the losses I talked about last week, and I just sort of lumped them all together for you with a few sort of coefficients, a few factors, but I'm going to explain those a lot more in detail. Now, just let me know if everything's going well on the live stream, that you can hear me. Yeah, g'day Wayne from Melton. G'day Raymond. I see you got the link. That's good. And yeah, just let me know if audio's good, video's good. In case I'm talking to a room full of silence, or you're listening to a room full of silence from me, that would be no good at all. So yeah, what else? So things like MLPE, what on earth is that? MLPE, module level power electronics, but talking a bit about how they can help with things like double peak arrays, and it's kind of code for some shading, and the effect of azimuth and inclination on the performance of a PV system, and why south is the new north. Yeah, that's an interesting one. Yep. Also a bit about what good is a battery for you, and why self-use is always the best strategy. So there you go. That's kind of what I got lined up for you today. And I'm just going to check my chat. Everything's working here. All perfect, says Duga. Thank you. That's very, very reassuring. Yeah, so DJ Glenmo was otherwise engaged, so yeah, he sent me today. Apparently, he quite likes having me on because I can do the deep tech stuff. He just kind of waffles on and plays music and tunes and things. So yeah. Also, I did hear that he said there was going to be a guest this week, but actually, I believe the guest fell through as well. Nothing serious, but that guest might have to be rescheduled. So there you go. So Charles says, I'm getting a wood burner installed tomorrow. So rearranging the arrays. All right. So you're going to have a chimney right in the middle of your arrays. You're going to be probably one of the candidates for a double bump or a double peak maximum power point. So I think you might actually experience this phenomena. Now, let's see if I've got I forgot to turn the overhead camera on. Hang on. Which means I also need to focus it. Probably. Yep, need to focus it on something. Yep. Where's my focus assist? Hang on, got to get the focus assist tool. today was all a bit of a rush, actually. So, Professor Glenmo has family duties as well, and they sometimes occupy a bit of time, feeding children, all that sort of boring stuff. So there we go. Now, let's see if I can get that focus before I cut over to my overhead camera. Nothing worse than an out of focus picture. That looks pretty good to me. Okay. All right. So let me bring something up here. Now, I've been pretty excited with what can be done with Python. Now, I'm no, code hero. I'm really more of a AI hero, using AI to do a lot of the grunt work for me. But what have I got here? Trying to get my keyboards in the right place. The power of Python is amazing when it comes to solving graphical problems, mathematical problems, etc. So let me just get this little one up here. And where are we? So you can see it. Get my overhead. All right, so you should be able to see my little layout here. That's what I'm looking for. Interesting, yeah. Why am I mentioning Python straight away? It's because I used it to generate all these drawings here, all these charts, and I thought that's pretty cool. Normally I'll do the hand draw them, which takes me ages, but I can just write some scripts and it generates them and I can print them out. Now, I could have used generic ones from or commercial ones from particular data sheets, but I just want to talk generically about IV curves and understanding them. So why are we going here? Well, the fact that a solar module is actually a kind of a non-linear current source. What I mean by that? Well, it's got, non-linear power source. It's definitely a linear current source. That means if you double the solar radiation, you double the output current. But when it comes to power, it's not linear. And the reason for that is the load line, which is this blue line here, is the operating line of a solar. In this case, it's just a single solar cell. The same would be for an array. Now, if I identify my axes here for you, on the y-axis, we've got current in amps. I'm trying to position this so you can see that. So over here, we've got current, and across the bottom, we've got voltage. Now, remember, this is a single cell, so volts are pretty low, but it's actually in an ideal cell. There's no such thing as an ideal cell. So you won't actually get 1 volt out of a silicon cell, more like 0.6 or so, but this is an ideal cell in terms of its voltage output. So why is this load line like this? Well, it's the physics of silicon. And what it tells us, at different voltages that the cell's operating at, we'll get different currents. And there's going to be, as many of you will know already, the rule for power is voltage times current equals power. So the plot below here is the plot of power. And you'll see that it actually peaks at this point here. We call this the maximum power point, funnily enough. And it's often abbreviated to just MPP, so maximum power point. Now, it looks like it's a fixed point on this this chart here, but it's not actually fixed at all, because it varies with conditions. It varies with temperature and it varies with irradiance. So irradiance affects the output current of a PV module fairly linearly. Above a sort of really fairly gloomy day, when you've got like 100 or 200 watts of solar radiation. But once you get above 200 watts or so, up to 1,000 or more. And by the way, 1,000 is the test condition, but it's not an absolute. Here in Australia, we get some beautiful peak days. I've seen 1,150 watts per square metre on a meteorological grade solar radiation meter I've got here. So it can get higher. So this curve would be at different irradiances, slightly different. So I'm drawing some different versions of the same IV curve. So this might be at 800 watts per square metre. This might be 600 watts per square metre, etc. You get the idea. And so as you go down in terms of radiance, so that your IV curve starts to flatten out a little bit. That also means that the power point moves too. So the power point doesn't stay in the same place. It will track about in terms of its position in respect to the operating voltage of the array. So what do we do about finding out where the maximum power point is? Now, this is one of the great Australian inventions. It's called the maximum power point tracker. Yes, it's an Australian invention. What else are we famous for? The stump jump plough, the humidity crib, Wi-Fi, and the maximum power point tracker. That's an Australian invention by Stuart Watkinson back in 1983. He didn't invent the theory, he made the first commercial versions. So in Queensland, a young graduate at the University of Queensland, he made the first commercially available MPPTs. In fact, I've got one right here. Hang on, I'll show it to you. It's kind of nice having all this stuff on hand. So there it is. Look at that amazing piece of technology. This actually is not the one I had, but I had one identical to this running my home back in 1991. And it was a revolution to me, and a revelation in terms of how I could improve the performance of my solar array. Back then, I had the huge sum of, I think it was initially 3 80-watt SolarX modules. Then I bought 3 more at the enormous price of about $800 each, and I had 6 of them, and they were nominal 12-volt modules. So that means their VOC will be up around 18 volts or so. Around about 20, 21 volts. VMP around about 18 volts. And it meant charging a battery system. I had to series them up to sort of be approximate what the battery was. So it was a 24-volt battery system, so we tried to put 2 panels in series. But there was quite a lot of loss at that relatively low PV voltage. And so being able to use something like this, where you could run your PV array at a higher voltage than your battery. Now, that's one of the advantages of a maximum power point tracker. It's also a DC-DC converter. So it matches the battery voltage to the array voltage, and they could be different. So there you go. That's the actual device that Stuart Watkinson built. And he built them by hand himself. AERL, Australian Energy Research Labs, they're still in business. In fact, behind me, I've got 2 more of theirs, 2 more later versions, and they're making an excellent MPPT in Queensland right now. There's one of the very few that's suitable for arrays up to 600 volts. And has built-in earth fault detection, which actually is mandatory in 5033. Once you get over 120 volts DC on your array open circuit, you need to have earth fault detection. And there's only a handful of charge controllers that can do this. And literally, I can think of only 3. So AERL were one of those 3. So it's a really big plus. But MPPTs are also built into inverters themselves. So inverters have one or more MPPTs on their input. So what's the big deal? Why is this MPPT thing so exciting? And let me just put down this very precious device. Well, they do more than just match the array voltage to whatever the power conversion equipment requires, or in case of a battery system that's DC coupled, the battery requires. They allow you to find the maximum power point. So let's go back to my little diagram here. So I said that the maximum power point was here, but then I went on to say that actually it moves around with irradiance and with temperature. So how do you find it? Well, it's a little algorithm called perturb and observe. Perturb means change stuff, and observe to see what the outcome is. So when an array first sees sunlight, its voltage goes up. And so it goes up to open circuit because it's not drawing any current yet. The charge controller or the MPPT can determine when it starts to draw current. So it's effectively a smart load. So it starts here at open circuit. So we'll call this open circuit conditions, and it then starts tracking along this line. And what it's doing is it's lowering the voltage and seeing that if the current increases. And it's doing a very clever thing. It's going volts times amps equals power. Am I getting more power? If yes, keep going, keep going. So that's the perturb and observe phenomena. And at some point, it goes, uh-oh, I went too far, go back. And so it hunts around this point continuously because this varies dramatically in real time. So if you've got some high cloud that scatters across your array, your PowerPoint will move quite quickly. And so the tracker is constantly trying to find the sweet spot on the array. So that's a very useful function of a maximum PowerPoint tracker. Now just checking the chat here. Mark, g'day. Hi, Mark. Nice to have you on there. Mark Kavanagh, fellow YouTuber from MC Electrical. He does some great content. And I've got Yakety90, and he says, I'm writing up an ARL Earth Guard with a Victron and an Earth Guard with a Victron 250. That's right. So ARL actually makes standalone Earth protection device or Earth detection devices, Earth fault detection, sorry, and it's called Earth Guard. So you can compare that with an existing MPPT. In this case, Yagedevi's doing it on a Victron 250/100. In Victron speak, 250 means the maximum voltage, and after the slash is the output current, so 100 amps. So good timing, eh? Yeah, indeed. So let me just explain, what did we do before we had MPPTs, maximum PowerPoint tracking devices? And not that long ago, before 1983, what did we do? So let me get a bit of blank paper here. Got lots of bits of paper. Where's a blank bit? Okay, what we did was, now this is going to sound awfully crude, but we started off with very simple systems. A panel, like this, and a isolating switch, and a battery. And typically that would be a lead acid battery. And that is actually a switch. And it's really just for turning off the solar. Now, the problem with that is, if you don't turn off the solar, you could overcharge the battery. That's problem number one. Problem number two is if you leave a solar panel directly connected to a battery, at night time it becomes a load and it slowly leaks away some of the power that you put into the battery. So some clever person came up with the idea of actually putting in a blocking diode. So what we've got here is a blocking diode. And so it only allows charge current towards the battery. Sorry, of course there's two wires, and so we'll call that the negative, that's the positive. There we go. You can put the blocking diode on either, didn't matter. So now you've got a way of turning it off, and you've got a blocking diode, but you've still got the problem of overcharging the battery. And so if this battery wants a maximum, say it's lead acid, 14.1 volts, but this is a nominal 12-volt panel. A nominal 12-volt panel have a VOC up around sort of approximately 21 volts. It will overcharge this battery. Its VMP is going to be up around 18 volts or so. So it'll still overcharge this battery and cook it. So what happened next is someone came up with the idea of slowing down the current flowing into the battery. Now, I've drawn a switch again, and you go, oh, what's that, Glenn? How does that work? It's not an ordinary switch. This is a pulse width modulation device. Basically, this is a semiconductor switch. So it's switching very fast on and off. And how does that help? Well, Charles will know this intimately. So Charles and I, both from the telco world, is that the interrupting a current or a source for a moment. And so you turn it on, you turn it off. You turn it on, you turn it off. And you gradually reduce the amount of time that it's on for versus off. Now, what I'm drawing here is current here and time across the bottom. And therefore, the average amount of current is falling. The average current is going like this, down and down and down. And so I can slow down the amount of current to the amount required by a battery for just equalization, right down to actually turning off the current altogether. Now, these pulses are actually happening at high speed too, so typically in the kilohertz range. But there's still a problem. Even though this now solves two things, it solves the reverse flow at nighttime problem because it's a semiconductor switch and it can be effectively a diode as well. So it could be a blocking device. and it also solves the overcharging problem by limiting the current flow as the battery approaches its target voltage. We've still got a bit of a problem, and it comes back to this chart over here. It's about the power curve. Now, if I was to draw this with a 12-volt panel in mind, I would say this point here might be, let's call this 18 volts. So that's our volts at maximum power. Now, we've got a 12-volt battery, and so 12 volts is going to be about here. All right. With a pulse width modulation device, you are stuck at this point. You are stuck at the battery voltage. You can't actually get up to 18 volts on your array, so your panel can't get to 18 volts, so it can't get to its maximum power point. So you're operating your panel at a less than ideal voltage. It's not bad, it's just inefficient. And it actually gets worse because a 12-volt battery might start, let's say a lead acid battery, 10.5 to say 14.3 volts might be its range, right? When do you most need to charge the battery? When it's empty, right? And that's when it's at 10.5 volts. So you're actually operating way back here when your battery's empty. You're getting the worst possible conversion of sunlight into electricity because of the poor voltage mismatch. So that's one of the reasons that a pulse width modulated charge controller is not nearly as efficient as a maximum power point tracking charge controller or device. However, there is a perfectly good reason for PWM, pulse width modulated charge controllers, to be around, is they're simple and cheap. And if you've got, say, something, a little camping setup, one panel, it's just keeping your battery alive on your RV or your caravan, you don't actually care about getting the maximum power out of the array. You just want to keep the battery charged up when you're not using the vehicle. And so for a relatively modest $10 to $20, you can probably get a PWM charge controller. So they still have a role for those small applications. So there you go. The history of charging from when we used to do it with a switch, with a blocking diode, and we moved on to PWM and more recently to maximum power point tracking charge controllers. Okay, so what are we looking at here in the question land? Just checking. Yakiti says, I'm looking to use it to trigger shunt trip breaker for a 24-volt DC supply, so when EarthGuard triggers it, it can shut down the main DC isolator. Oh, very clever. Okay, so you're basically turning a detection into an interruption. So even though the standard actually requires fault detection, interruption would be a nice thing as well. So very, very clever. All right, so what next? That's Ivy Curve land, and let's go into talking a little about the characteristic of a PV module under temperature changes. So what have I got here? That's the wrong one. Here we go. Did it fix the temperature on? Okay, good. Got one here. And someone asked the other day, those Python scripts that I used and the ones I've used today, are they available? Yes, I actually put a link in last week's description for the ones that I showed last week, and I'll put a link for the ones I used this week to generate all these. So if you're into coding, you can freely use those. I have to credit DeepSeek for helping me produce them, by the way. DeepSeek is another AI platform. It's free, it's fast. You can even run it locally on your device. I've got it running on my laptop, so when I'm on a plane to nowhere, I can actually still use AI. It's pretty cool. You need a fair bit of hard disk space, though. It takes up, I think the language model I've got takes up about 0.5 terabyte of the hard drive. So what am I up to here? Okay, so a solar panel is often rated in watts. So you might hear someone say, oh, we've got 440 watt panels on our roof. What that means is at test conditions, and that's 25 degrees Celsius cell temperature and a radiance of 1,000 watts per square metre and an air mass of 1.5. And if you're wondering what on earth is air mass, basically it's how much atmosphere does the light have to pass through to get to you. So, if I was to draw the Earth and then draw the atmosphere as massively exaggerated, because by the way, it's only like a tiny skin around the Earth. And if the sun is here and my panel is here, it's only going through one atmosphere, 1 AM, right? But panels are tested at a more typical, which is the sun rises and sets. So about half the time, it's not perpendicular, and of course this varies with the latitude that you're at. So now we've got a greater distance. So we've got 1.5 air mass. So what does air mass mean? It's actually about the colour of the light. So the more that solar energy passes through the atmosphere, it will be absorbed by the different particles in the atmosphere and effectively change the mix of a spectrum. So it gets to move a bit more to the warmer end of the spectrum, and that has an effect on the performance of a solar panel. So solar panels have a spectrum sensitivity, and depending on the cell types and other manufacturing features, that sensitivity can be biased one way or the other to the short or longer wavelengths. And so for a standard test conditions, they go, bugger it, we'll just choose a typical 45-degree angle sun coming through through space, through the atmosphere, and that's what we use for testing solar panels. So there you go. Okay, I told you it was going to be a bit techie, because that's what Professor Glenmo does. He does techie stuff. So what am I telling you about this 440 watt module? Well, it's open circuit voltage, power output, Oh, I've got the wrong table here. But anyway, this will do, because I'm going to go through a few of them. You might think you've got a 440 watt module, but actually it's got a temperature coefficient for power. Now, that means it's a negative coefficient. That means as temperature increases, power decreases. And how much it decreases by is this coefficient. So in here, I've shown 0.4% per degree Celsius from test conditions. So that's standard test conditions here at 25 degrees. Now, I have to point out this is cell temperature, not ambient. And this is a big gotcha, because cells of a PV module perform or act similarly to metal in terms of their response to irradiation. They'll heat up pretty quickly. So you might have an air temperature of 25 degrees, but once you put 1,000 watts of solar radiation onto them, they'll be way above that, typically 25 to 35 degrees hotter. And we'll talk about how you calculate that in a second. So this is unlikely to be true unless you live in a very cold place and have full sun. And when I say very cold, I'm talking that you're sort of around the 0 or sub-zero mark and it's full sun. So at this time of the year, you might be getting close to that. In fact, we had some really fantastic performances out of our trackers recently, and it was about 5 degrees Celsius, and we were seeing close to the peak rating of the panels, which is pretty rare. But it's nice to have occasionally. So how do we work out what the real power of our 440 watt module is under real conditions? Well, you could say, let's find out what the worst is. And so how hot does it get where you live? So we're going to find out what the ambient temperature is. So let's say the ambient temperature is 40 degrees, right? So here is our ambient temperature. I can't spell ambient, but there you go. Hang on, I've got to write it properly. Ambient. I'm a bit dyslexic, as professors often are. That's my ambient temperature, 40 degrees Celsius. But then I've got 1,000 watts per square metre of solar radiation shining down on my panels, and they're going to heat up. How much will they heat up? This is where the famous rules of thumbs come in. Well, just the one rule of one thumb. So if the panels are elevated from the surface that they're mounted on, they'll benefit from both any air movement due to wind and also really good convection. So they'll convect heat away from the rear, and they'll sort of self-cool quite well. So around about 25 degrees above ambient. So ambient plus 25 degrees Celsius. Sorry for those who think in Fahrenheit. I can't think in Fahrenheit. Is what you would get with a tilted array, or tilted away from a roof or freestanding. Where if you've got panels parallel to the roof, as they are typically installed, so with mounting rails parallel to your roof, and you've got around about 150 mils clearance between the back of the modules, you'll get about 30 degrees above ambient. And if you lay your panels horizontal, you've really stopped the passive convection that would occur. And so they'll be more like 35 degrees above ambient if they're flat on a surface. So let's go for the middle one. Most commonly, people will be putting panels parallel to the roof. So if the temperature is 40 degrees ambient, we're going to add 30 degrees to that. Yeah. So we're up here somewhere. So this is the cell temp on a hot day. It's 70 degrees. Panels can take that. In fact, if you put your hand on a hot day, you'll know it's really, really hot. So at 70 degrees. So how far away are we from test conditions, right? We're a long way. We're 45 degrees away from test conditions. That's pretty bad because 45 degrees Celsius difference, so we call this delta T, change in temperature, is 45 degrees above, okay, our test conditions, and we multiply that 45 by our coefficient for power loss. Now notice it's a negative number. So all those smart maths heads out there will know that a negative number times a positive number gives you a negative response. So it's going to be a negative answer. So we crank out the big calculator. See if I can get my calculator up. Okay. And I can't, what am I doing here? I don't want, I've got temperatures for some reason. I want, what have I done with my calculator? Clear history. I've got a faulty calculator. I can't get it out of temperature. This is really annoying. But anyway, hey, why don't you guys help me? So let's do this really complicated sum here. So we'll take 45 degrees. It's a positive number, and we'll multiply it by negative 0.4%. That's how much change we'll get. And the answer is, I think it's about 18%. Anyone agree with me? I'm just trying to do it in my head. So I'm looking at the chat. It takes about 20 seconds between when I say something and when you hear it. And if you hear it and you can type in the answer, that would be great. But I'm really flummoxed by why my calculator's stuck in temperature. Why is it stuck in temperature? I want to get it out of temperature. I'll give up on that. So that's how much power loss we're going to get at 70 degrees Celsius. So that's really a worst case scenario where you have got a really hot day. Your panels are not working nearly as well as you might think because of this rating here is nowhere near true. And so up at 70 degrees, we're going to be somewhere around here. So our panels will be, if I draw a line across here, operating around about 360 watts. So our 440 watt panels put out 360 watts. Now, this is something you can baffle a customer with or with a friend when they say, how come my 6.6 kilowatt PV array that I paid so much money for never puts out 6.6 kilowatts on a beautiful sunny day? You should say what you want is a beautiful freezing cold sunny day, and you might get close to it. Yeah, so there you go. I found the result. Oh, here we go. I've got to turn off convert. Okay, so I'm obsessed with getting this right. So times, now some calculators won't do multiplication by negative numbers. They'll just always give you a positive result. But look, we'll just pretend that, and therefore 18% negative. So that's power loss. Oh, I was right. There we go. Professor's a savant. He can do basic arithmetic in his head. Okay, so that's temperature effects on power. But let's look at something else. All right, how are you going out there, by the way? Haven't seen any more chat. Hope I'm still coming through loud and clear. Now, that example, by the way, was drawn from I should go back to it for a second. That example was drawn from a module that has a temperature coefficient of 0.4%. But that is terrible. These days, modules are much, much better. In fact, one of the improvements in solar panel technology has been reducing the amount of lost power due to temperature. So that coefficient is much better now. And I looked up some ICO 440s just because I had the data sheet handy, and they're 0.25. That's way, way better. I think that's right. I think they were ICOs. But anyway, 0.25 is more typical of your quality solar module. So that's one of the things you get with both improvements in the technology over time, but also, your quality products have less power loss due to temperature. And so that curve is or the gradient, is a lot flatter than for 0.4. And so up at 70 degrees, if I go up 70 degrees and go across, I'm up around probably over 400, let's say 410 watts. So up from 360 to 410 watts, just because of the temperature gradient is much gentler. There we go. So what's next? And open circuit voltage is next. Yep. Okay, let's go to that one. So why am I concerned about open circuit voltage of a PV module, given that that's not a useful condition? It doesn't produce any power when it's in open circuit. So it is a condition that occurs every day. And it's one of the most critical numbers when it comes to, do you blow up your inverter or not? Yeah, it's the blow-up voltage. So inverters and charge controllers will have a maximum input voltage that they can withstand. It's often to do with the filter capacitors across their input. And filter capacitors tend to come in round numbers, you've got a 500 volt filter capacitor, a 550, a 600, etc. And they may put a little bit of headroom in there if they're being kind to you. So they might put in a 650 volt capacitor and or a bunch of capacitors, and they tell you maximum is 600. But that is not a lot of tolerance. So you need to be aware that under certain conditions, the voltage from a PV array will go quite high. In this case, it's also a negative coefficient, but now we're worried not about a hot day, we're worried about a cold day. Because on a cold day, you'll go above the STC, above the 25 degree test temperature. So there's our standard test conditions. And depending on how cold it is, and so for this module with this is the ICOs, by the way, I remember doing this one, they have a temperature coefficient of open circuit voltage of 0.22% per degree C. And what we need to know is how cold is it? What's the coldest possible operating temperature? Now, you could say, typically around here it never gets much below zero. It's probably you folk up there in Brisbane. But you have to actually look at the extremes, because it could be the one day that it gets to -3 or -5 is the day that you blow up your inverter. So what my recommendation is, find from your meteorological service, NIWA in New Zealand, the BOM in Australia, or other services around the world, and also NASA have some global data too. What is the coldest ever temperature? And use that just to be sure. In fact, if you want to be sure because of climate change, put in a factor of, maybe another 10% on that. So here, where I live, it sometimes gets below zero, but not much. And I'd say maybe the worst case might be -3. So I'm going to choose -5 as my coldest ever possible temperature. And I want to know how much voltage increase I'm going to get. So from standard test conditions, what is my change in temperature, my delta T? Well, it's in the negative direction, so it's below test conditions. So it's actually 30 degrees below test conditions. -5 is 30 degrees below 25 degrees Celsius. So it's -30 degrees C of change. Remember, it's change. I'm not talking it's -30 degrees outside. I multiply that by the coefficient. So I multiply that by -0.22%. Okay, and that's going to tell me how much. Now, a negative times a negative, those maths whiz out there will know that's a positive number. Okay, and let's find out what it is. So 130 times 0.22, it's going to give me 6.6% increase in voltage. on top of whatever the module voltage was. So at standard test conditions, it was 40.5. So I'm going to increase it by 6.6%, and up we go. So in this case, I think I calculated it for minus 10. So it went up to 43.6 volts. Remember, this is one panel, and you might have 12 of them altogether. So let's see if we've got, let's go for 13. So 13 panels, and at minus 10, they go up to 43.6 volts. And, I'm up to 566 volts. So getting up there to that 600 mark, which is where a lot of inverters actually, single-phase inverters, top out. Three-phase inverters generally have a higher maximum input voltage because they work more efficiently with a bus voltage significantly higher than a single-phase inverter, so they want the volts. They want to be up there in the 600 or 700 mark or even more. So there you go. So that's the effect of temperature on open circuit voltage. Okay. Oh, g'day, Scott. Hi from Giro. Good to have you there. And g'day, Vaughan. Yes, you're late, Vaughan. I'll mark you as late. Good to have you there. And Yageti says, I take it this 440 watt panel is not bifacial. I'm aware it's a different calc due to the ability to cool better from double-sided glass. Okay, so that's another whole tech talk, is bifaciality and calculations based on 5033, our PV array standard for bifacial panels. So I might just skip trying to explain that in a jiffy. It's a bit more complicated. But yes, you're right, Ikadevi, we do have to consider with bifacial panels there are different factors. So now this is another little explainer table here. And so what we're looking at is when you look at a data sheet, they'll give you ratings at STC, standard test conditions, but they'll also give you them at NOCT, normal operating cell temperature. Now, what on earth is NOCT and why is it different from STC? So this is an effort to give a more realistic number, NOCT, or a more realistic operating number for someone who lives in southern Germany. Why do I say that? Well, instead of using 1,000 watts per square metre to test the panels, for NOCT they use 800 watts per square metre. That's because in the northern hemisphere there is more atmospheric particles and pollution basically, and irradiance is suppressed more than it is in the southern hemisphere. So woohoo for us in the southern hemisphere, we get higher solar radiation. So far so good. And the two climate systems, the circulating, don't really mix. So you've got different rotational directions in the northern hemisphere to the southern hemisphere, and they don't really mix together. So we're kind of lucky down here having a higher peak radiation. So 800 watts per square metre. Also, with a cell temperature, an ambient temperature of 20 degrees and a test cell temperature of 45 degrees. So assuming a summer's day in southern Germany, it's a beautiful hot 25 degrees. Though I shouldn't joke because actually they've been having heat waves. So yeah, it's been pretty hot. So that's what NOCT is, more typical of operating conditions than standard test conditions. But I generally tell my students, just don't worry about NOCT because you can calculate everything from this number here and you can derate for temperature and irradiance, etc. So yeah, it's kind of like a feel-good number that you can go, I thought I'd get 33.5 volts off my panels, but actually 31 point something is more typical. Now, the other reason to note the difference is that you might have a very small PV array. You might have like 4 or 5 panels in series connected to a string inverter. And string inverters have a startup voltage. Basically, they'll want to get to a certain open circuit voltage before they'll even start drawing current. And so, figures around, say, for a single phase inverter, 120 volts, 125 was fairly typical for a startup. And when I say startup, at that point, they'll try to draw some current and immediately there'll be a bit of drop in array voltage as it tracks along the load line of the IV curve. And they may track down to 100 or even 80 volts and still keep working. But at some point, they just give up and say, it's not enough to be worth trying to generate. We're just not efficient at all. It's time to go back to sleep and wait for the voltage to climb. But if you've got a very small array, you may have very minimal peak voltages under typical days, and you might barely struggle to get above that startup voltage. So in summertime, for instance, your inverter might not even turn on. Now, this true story, I actually know of someone who had this problem. They were complaining that their inverter was installed in wintertime, it worked fine, and come summer it wasn't turning on. And I think they had a Sunny Boy 1100 with 5 panels in series, and it just wasn't enough voltage in summer when the panel started to lose voltage due to temperature. So yeah, that's why long strings are good. In fact, generally solar inverters are more efficient the further up you go in the IV curve. In the power curve. So if I haven't actually prepared a drawing for this, so I'll just have to do it myself. If I draw the power curve of, and I'll do this in percentage. So that's 100% power. Okay, and this is efficiency on this side. And so we might be 100% efficient, and our power curve might look like this. And if I'm probably starting here at something like 80%. So you can see that it climbs pretty quickly until it gets up to, and these days for string inverters, it's generally north of 95, sometimes, let's call it approximately 96% efficient, because they're pretty damned efficient at converting solar DC into AC. And that means we're on the game, we're hitting that peak efficiency. But in terms of power, so we might be up around the sort of 25% mark before we actually hit peak efficiency. Now, if you've got a inverter that's, let's say you've got a 10 kilowatt inverter, it's not you actually producing about 2.5 kilowatts of PV power. Are you up in the efficiency part of the curve? So you can underpower your inverter. So it's a good reason to actually have more PV than your inverter's rated for, because you're always going to be high up in this power curve, this efficiency curve for power. You're going to be right up the top there most of the time, even on overcast days. So there you go. That's where you don't want to be, in this quadrant here. And when you look at the data sheet for an inverter, they often give a peak efficiency and an EU efficiency. EU basically means they break up this into segments like this, and they weight each segment and average them and come up with an efficiency over the whole day. And it's always less than the peak. So the EU efficiency might be 94.5, whereas peak might be 96. And so it's a more honest representation of the efficiency you could expect. Just one other note too. Now I've drawn this curve here, I just remembered last week, I was talking to you about standalone power system design and how battery inverters with basically toroidal transformers inside them are generally less efficient than string inverters, which are transformer-less. It's partly because in this part of the graph, they've got quite a lot of self-consumption. So a large, it's often due to eddy currents in the transformer and thermal losses. So a large toroidal transformer might be gobbling up the first, 5% all the time of your production. And so you're losing the first 5%. So that's why their efficiency is not so great at low power levels. You want to stay well away from the low power levels for efficiency reasons. But then again, you want to stay as low power as possible for days of autonomy. So it's a tough one to pitch. But anyway, you just live with it and accommodate the fact that your battery inverter is probably somewhat less efficient than a string inverter, and you need to factor that in your losses in your design. Wow. Geez, haven't I been talking for a long time, and just on a couple of little pictures there. So checking the chat, nothing in the chat there. Okay, so what have I got for you next? Temperature. And we've covered that one. I think I've covered that one. Oh, yes. Okay, now it's time to go to my little list. And so if I can bring my list up of stuff I had to tell you. Okay, boy, this could be a long session. So we've covered IV curves, and what I was going to tell you about, which is kind of the highlight, number one, was the double peak MPP, maximum power point with a double peak. Oh, excuse me, that's lunch. Let's have a look at IV curve again. Now, everyone probably draws IV curves like this because that's what you see in the data sheets, right? And that is, this is current and this is voltage, open circuit, short circuit. And then between those extremes, we'll have a maximum power point like there. So we'll call that VMP. And we'll have a maximum current at maximum power. And so that there is the sweet spot. That's our maximum power point. And if you were to draw on another secondary y-axis, you could draw a power curve that goes like that. And that would be power. Okay, all very well. But a double peak MPP is when you've got some perturbance in terms of the panel's performance in a string. So you've got, let's say you've got 6 panels, and as Charles is doing today, he's putting a chimney right through the middle of his array, and so it's going to cast some shade on one of those panels, or 2 of them maybe, depending on where he puts it. And so that panel is going to be suppressed a little bit in its production. It may even go into complete bypass, which would be a shame. What you can get when that happens is, I'll probably use a different colour, is an IV curve that looks like this. So you actually get 2 bumps or knees on the curve. And remember I told you that a maximum power point tracker starts by going along from open circuit voltage, trying to find the sum of volts and current being the greatest, and it'll get to the first bump and it'll go, I found it. So we call this the local maximum power point. And it stops there. But it might turn out that actually that one gives you more power, but it never gets there. So this one we call the global maximum power point. Now, some inverters have a function where they will sweep this curve periodically, pretty fast, and find the global and ignore the local. So they're very good at squeezing a bit more out of your array, even when you've got some disturbances like shade. Or you may even have a mismatched module. So if you've got one of your modules got broken with hail, and you changed it to whatever you could get it, and it's a different power rating or whatever, it will actually cause this problem as well. Or even a faulty module itself with some, say, micro cracks in the cells, it'll effectively operate like a smaller powered module. So inverters and charge controllers that have the ability to detect the global peak give you a bit of an advantage there. But there are other solutions, and one of them is MLPE. Now, here we are, just checking my chat here. So, yeah, Mark, don't squirm too much. I'm going to talk about microinverters and optimizers. Generically, MLPE stands for module level power electronics, and it's could be a DC-DC device or a DC-AC device. So let me just show you how this works. There's one module, there's another module, here's another module. Now, typically in a string system, they're connected in series. So, the positive ends, and the negative ends like this, and you just connect them in a daisy chain, right? But with MLPE, you can have a device that sits between the module and the string, like this. So these are MLPE devices, and therefore we've got a string like this. So that's the string, and that is the MLPE, module level power electronics. Now that could be, if I call this a DC string, so it's going off to a regular inverter, these would be something like converting DC to DC. So something like, to use brand names, Tego, so Solar Edge with their optimizers, and Huawei with their optimizers, and there's other brands out there as well. But they make a DC-DC MLPE device that goes on every module. By the way, it also can give other advantages, other than the fact that, well, I haven't told you what the first advantage is. It means each module works independently and contributes as best it can to the DC string. So you might actually have a 440 watt module here, and a 350 watt module here, and a 100 watt module here. This one might be a VMP of 33 volts because it's new. This one might be a VMP of 40 volts because it has more cells in series. So everything's different on every module, and this one might be a VMP of 18 volts. It doesn't matter because the DC-DC converter will make sure that the string voltage is optimal, and each module will be doing its very best. So we've got a maximum power point tracking charge device in every one of those MLPE, every one of those DC-DC converters, or more correctly, they're called DCUs, DC conditioning units. That's the term. So we'll call that a DCU. That's what they call them in 5033. It also means that if you've got shade on part of one panel and it's underperforming, it doesn't sacrifice anything with the other panels. They work as best they can. There is another approach. I won't draw the whole thing again, and that is to use DC to AC conversion, commonly called a microinverter. And so now we've got an AC bus. So this is our AC bus. Let's say it's single phase, so it's a 230 volt nominal, but we've got DC coming in. So we might only have a VMP of 33 volts DC, but we're outputting 230 volts AC out of every module. So it gives you pretty much the same advantages. It means that you've got each module working as best it can, shade tolerance, mismatch of modules, not a problem. And so for installations that are, have difficult location requirements, so a chimney in front of some of your panels, Charles, that's when one of these two solutions can come to the fore. Now, I can probably hear people shouting, oh, but what about the cost? The cost of solar panels now is so low that these devices are actually probably as much or more than the cost of your panel. Why not just spend the money on more panels and stuff the losses? I'm personally a bit of a fan of that approach, which is the answer is always more solar panels, and it'll overcome some of the losses due to things like shading, etc. But if you're a bit of a efficiency geek, this will give you the greatest efficiency out of your system. I know, Mark, that you've done some testing and it wasn't all that dramatic. So Mark's got a YouTube channel, MC Electrical, and he's actually done some testing on shading of string inverters and ones with microinverters, I think it was, and seeing what the difference was. But there you go. You get a lot of data too. So if you're a data geek, you can actually see how every panel's performing. Personally, that's a problem when it comes to customers because they know too much. You think customers should know everything. No, not necessarily, not unless they know what they know or can be properly informed with what they know. So you end up getting complaints. I'll say, panel number 2 is not working as well as panel number 1. And you go, can you take a picture, please? And there's a great big tree in front of panel number 2. So, yeah, it's shaded. That's why it's not working so well. I know that companies like Enphase actually charge a premium for module level monitoring. Well, they used to. I don't know if they still do, because of the number of support calls that were nuisance based on people not understanding how panels work. But there you go. Okay, so Yagiti's asking me 10 kilowatt multiplus with a 10 kilowatt Fronius and a 5 kilowatt DC coupled MPPT inverter allows for 25% derating inverter for temp if required nominal output. Yeah, I'm not sure what you're asking me there, but yep, sounds good. Charles says that's what I'm doing. Tegos, but my place is one where you wouldn't want to install solar anyway. Oh, okay. Well, maybe this is our chance to go to my last points, because I think I've run out of time, is why is south the new north? Okay, it's a pretty radical statement. Is south the new north? Now, I'm going to have to bring up an Excel spreadsheet for this. People get very kind of biased towards what's a suitable roof. I'll go, my roof's not suitable because it's got shade or it's not facing the right direction, and so I won't bother putting solar on. But actually, a roof with no solar panels is not suitable for generating any energy. Putting solar panels on basically any surface that can see sunlight is going to give you some benefit. Whether it's a financially sensible thing, that's another question. And let me see, where are we? I've just got to bring up a table in Excel, and I'm in the wrong folder. Okay, yeah, student resources, here we go. Solar radiation data. Okay, so I'm going to choose Manukau, just because that's where Charles lives. Well, not quite. He's a bit north of Manukau, but it's Auckland anyway. And see if I can make this a bit bigger. All right, and share it with you. So see how we go now with that. Okay, so what I've got here is, I'll bring it over a bit, is solar radiation table. See, I'll make it as big as I can. Turn off that, stretch that, go plus one more. A solar radiation table for a particular latitude and longitude, so in this case it's Manukau, Auckland, and it is the annual average solar radiation on a surface. Across the top is the inclination angle, so in degrees, so 0, 10, 20, 30, etc. Down the side here is the azimuth in terms of direction, like 0 is north, so 0 is north, and 180 is south. So let's take, Charles, I don't know if you can tell me, but what pitch is your roof? Don't worry which way it's facing, what pitch is your roof, but I've colorized it. I've used color syntax highlighting here. And so green is good and red is bad. So you can look at this and go, gee, what's the best combination? Well, I think about here, I'm getting 4.41 peak sun hours annual average on a roof that's facing slightly west, 10 to 20 degrees west, at a pitch of about 20 degrees from the horizontal. There's my sweet spot. So let's say your roof isn't that, and it's something, less attractive. Let's say it's facing south, but it's still at 20 degrees. It's not nothing. It's 3.47 peak sun hours. Now, if I try and calculate what the difference is in terms of percentage, I'll take the worst, 3.47 peak sun hours, divide it by the best, 4.41, and it's telling me that my south-facing array is 79% as good as my a perfect north-facing 20-degree array in terms of, or surface, sorry. So it's really only 20% worse off. It's not 100% worse off. So why do I say south is the new north? Well, a couple of reasons. One is it's there and it's probably empty. It hasn't got solar on it already. It hasn't got a solar hot water system on it. It hasn't got other roof junk. You've got a big empty south roof and you go, well, I might as well use it. Now, this is an annual average, by the way. So if you're off-grid, it's not so useful to talk about annual averages. You want to look at the variation with season, and this is when it really does look poor. So we'll go through to June, which is, for the Southern Hemisphere, the worst combination. And so our north roof is, north-facing 2.51. Our south-facing is 1.41. It's about 40-something% as good. So, yeah, south in winter in a off-grid approach is pretty poor. But then again, it's all about, is it economically sensible? The roof's there. Would it be better to do a ground mount system? Do you even have space for more solar anywhere else? So it's still a financial decision of where you put them. So Charles is at 15 degrees south. Oh, there you go. Really? Your south roof. So we'll go back to Charles's one just so you can see what that looks like, Charles. And I'll share these through a link in the description afterwards. And so it's south at 15 degrees. Oh, you're in this sort of zone here, somewhere between 3.8 and 4.7 peak sun hours. So I'd say probably about 70% good as your north roof. There you go. It'll be better in summer because the higher the sun is, the less difference it even makes between north and south facing. And of course, east and west is another whole story. East and west has got some special powers, but that's a story for another time. So I think we've run out of time today. I actually had more content than I could fit into the hour, so I think I'll have to wrap it at this point. But sorry, Charles, that's the graph I was talking about. You're down here somewhere in the 3.83 to 3.47 zone. There you go. And yes, as I said, Charles is a good example. He's already filled up the north roof, so his only choice is for more solar is probably a south roof, or if he's got other facets that he can put solar. There you go. Well, thanks for letting me fill in for DJ Glenmo. This is Professor Glenmo, is Cuzzy Bro from New Zealand, filling in one more time. So there you go. I hope you enjoyed today. And maybe I'll be back. I'll see if he'll let me come back because I quite enjoy talking about this stuff. Anyway, see you guys. He said to play some music. How do I do that? I have to press a button or something.
Come on. Oh. Come here, boy.